Hello everyone, my name is Linghan Meng. I come from Department of Computer Science and Technology, Nanjing University. It's my honor to introduce our work for you. The title of our work is Marrying Discrimination to Boost Comparative Testing for Multiple Deep Learning Models. Recently, deep learning technology achieves great success and has beaten human experts and traditional machine learning technology in many areas. Meanwhile, concern about the reliability of deep learning models has been raised, which calls for novel testing techniques to deal with new deep learning testing scenarios and challenges. The boom of deep learning technology leads to massive deep learning models built and shared, which draw developers to build complex models by reusing available deep learning models, achieving specific functionality. One statistic in the previous studies indicates that more than 13.7% of complex deep learning models on GitHub reuse at least one primitive deep learning model. These third-party models need to be tested locally in order to select the most suitable one. As shown on the left figure, for a given task, we can obtain multiple models online that can complete the task. So we need to select testing samples to test them, so as to choose a suitable model. But the current deep learning model test focuses on two scenarios, debug testing and operational testing, which aim at a single model. This prompted the birth of a new test scenario, comparative testing. It is different from the previous test scenario in 2 points. First, the testing object is multiple deep learning models. Second, the testing aim is comparing performance among multiple deep learning models. In order to solve the comparative testing, we designed the algorithm. First, we explain the started problem. For comparative testing, the key problem is that the test set is unlabeled. Due to the limitation of the labeling cost, we can only find a small part of the test cases from the test set for labeling, that's helping us to complete the multimodal ranking. Our basic idea starts from 2 points. The first is Modality Routing, as our algorithm has the precondition that all samples are unlabeled. To deal with the lack of actual labels, we employ Modality Routing to evaluate the actual labels. The second is item discrimination, which is widely used in test analysis. We use it to evaluate the degree of differentiation of test cases to the models. Next, we will introduce our algorithm. The first step is to extract prediction results. We run multiple deep learning models against the testing context and get the prediction matrix. As shown in the figure on the left, we have 4 models and 4 test cases, and different colored shapes represent different predicted labels. After that, we get the estimated actual label through modality routing. We compute the frequency of predicted labels created by multiple models and choose the predicted label with the max frequency. For example, for sample 1, there are 3 models predicting it as red star, which accounts for the majority, so its estimated true label is red star. We can get the estimated labels of all samples as shown in the row L. The third step, we classify top and bottom models. We use the estimated true label to calculate the correct score for the model prediction. Then we set the 27% with the high score as the top class, and the 27% with the lowest score as the bottom class. In this way, Model 1 in the left figure is marked as the top class because Model 1 has the most predicted labels matching the estimated labels, and Model 2 is marked as the bottom class. Next, we can calculate the discrimination. The value of discrimination is the number of models with red prediction in top class minus the number in bottom class. As shown in the left, we get the discrimination based on the prediction results of Model 1 and Model 2. For example, for sample 1, the prediction result of the top class model is correct, and that of the bottom class is wrong. So the score is 1. Finally, we get the discrimination of each sample, as shown in the row D. Finally, we select samples to label according to the discrimination. We consider the samples with higher discrimination as the ones which are more helpful to rank multiple deep learning models. To eliminate the effects of outlier samples with higher discrimination, we introduce random selecting with 25% cutoff. We call our method sample discrimination-based selection, which is called SDS for short. Then, we present the experimental setup to evaluate the performance of our algorithm. We use the three datasets widely used in deep learning tests: MNIST, fetching MNIST, and w.r.t, and we found 80 models for the three datasets from the open source code on GitHub. Their model structure and accuracy are different. As comparative testing is a new testing scenario proposed in this paper, there are not existing baseline methods, so we found two state-of-the-art methods for comparison from current work on deep learning testing. The first is CES, which is an effective method to select samples for deep learning testing to assess the accuracy of the single deep learning model. The second is DeepGenie, which is a technique to help prioritize testing samples for deep learning models. We divided it into two baselines, DDG and RDG, according to whether there is random selection, and we also use simple random sampling, which is used as baseline for many studies. In order to compare the matching degree between the real multimodal ranking and the multimodal ranking of the test subset selected by the SDS and baseline methods, we use two indicators: Spearman's rank correlation coefficient and Jaccard similarity coefficient. Spearman compares the correlation between the testing ranking and the real ranking. The closer to 1, the more relevant. Jaccard compares the overlap degree of the top K models in predicted results and actual results, and the closer to 1, the better. We set K equals 10 in the experiment. We propose two research questions to organize our experiments. The first is for effectiveness, whether our method SDS can surpass the state-of-the-art methods in ranking multiple models. We compared the results of Spearman and Jaccard on three datasets. The green curve in the figure represents our method SDS. It can be seen that in all subgraphs, our method SDS is obviously better than the other baselines under all sampling size from 35 to 180. In order to show more details of the experiment results, we choose 6 sampling points as the representatives. The gray background means SDS wins, which is to say the Wilcoxon rank sum test p-value is less than 0.05 and the Cliff's delta is greater than 0.147. From the average value of each point, our approach is higher than all baselines and our approach wins other baselines at the most of points. So we can answer to RQ1. In ranking multiple deep learning models, our approach is significantly better than all other baselines in effectiveness. The second research question is for efficiency. Compared with the state-of-the-art methods, is our method SDS efficient? We choose the total time consumed when running studied methods with sampling from 35 to 180 in the table. We can see that except for SRS, our approach is similar to other baselines in time consumption. We summarize our work like this. First, this study opens a new dimension of deep learning testing, comparative testing for deep learning models, ranking multiple deep learning models under limited labeling efforts. Second, we propose a novel algorithm named SDS, which is an effective and efficient sample selection method for comparative testing. Lastly, we want to emphasize the importance of comparative testing and hope that more scholars will pay attention to this test scenario in the future. That's all for our work. Thank you very much.
Hello, everyone. Welcome to this session. My name is Grace Lewis. I hope you enjoyed the video, and I'll be chairing today's session. If anybody has any questions for Linghan, the presenter, please write them in the chat. Linghan, I would like to start with a question. I like the sample discrimination-based selection, the SDS approach, because it's very straightforward and simple. Can you clarify the choice of 27% as the threshold for top and bottom classes?
Okay. We choose the 27%, the top 27% as a top class, and the bottom 27% as a bottom class. It is used widely in the society, in the technology, but in the education research. So we choose 27% reference to the related work.
Okay. Thank you. So another question. So for the testing of the approach, you chose data sets that are very commonly used in deep learning research, right? You used MNIST, Fashion MNIST, CIFAR. So what are your thoughts on how the approach would scale to more real life problems? So in more complex scenarios, do you think it would even make sense to reuse models?
Okay. Thanks for the question. We conduct our experiments mainly on the deep learning models. We search the models mainly from the GitHub, which is open source. And we also try to use some simple models for our methods. And it is observed that our method also have better performance than other baselines in the simple models. So I think our method has the generation performance.
Okay. I'm going to see if anybody else has any questions. Okay, just a couple more seconds to see if anybody has any questions. So what was the most difficult part about the research that you conducted? What was the hardest thing?
I think the hard thing in our work is we search for a new scenario in the deep learning task. So we also write in the paper. We mainly want to introduce the new scenario for other peoples. So the another hard part for our work may be the model search. I think we may need more models for our work in the future work. Can you hear me? Okay. Thank you for the question from Marvin. How did you? Okay. Can you hear me? We select the models from the GitHub manually because and the models we select mainly connected to the task we want to and we mainly site selection criteria because we select the models for the task from for the three datasets, and they complete different classification task. And we mainly select models our main idea to set the problem is we want to identify the ranking performance for the models. So when we choose the models, we want to they have more different structures and more different accuracy. When we choose the models, we mainly focus on the accuracy and the structure they have. The more different and the more we choose.
Hello.